Thank you, everybody. I'd like to thank organizer Junling for the invitation. This is a wonderful workshop, and we have so many different topics, right? But can you hear me? Okay. But the underlying theme is the control. I guess more broadly is the system. So this actually, I was thinking, we had a terminology called system biology, right? We need to have a new name so control people can take credits. Really, right? We do everything, but people don't realize that's control. Right? Anyway, so what I'm going to talk about is also kind of like out of the mainstream. It's a variable selection. I have been doing this for a few years, and this kind of like a summary for the last year or so. Okay, let me just describe the problems. Okay, the problem I want to study is the follows. Given a system, and we have noise, right? It has some variables. In a typical system identification, so X are the past output and input, right? But does not have to be that way. So the goal is to identify or estimate F. That's my goal, eventual goal. The problem is that if dimension is high, Q is high, there are lots of problems. Nonlinear system identification is not easy, but dimension is high, we often end up with a problem, so-called the curse of dimensionality. That is something we have to deal with. And not because we are not smart. That's an inherent problem. Okay. And by the way, this problem, even though I characterize it in the framework on system identification, but if you look at the literature, it is everywhere, right? It's very small, but you can see in a pattern recognition, so this is called classify. You give me some input, I give you a class. Right? In machine learning, and also, for example, in imaging processing and in statistics, you have this kind of problem everywhere. Only difference is F is different. So this is a very general problem. And the curse dimensionality is also very general. It's not because of only system identification. Okay. Then question is, what do we do? System is nonlinear, non-parametric, at a very high dimension, and you want to solve that, right? So there are a number of scenarios. First one is the system is highly nonlinear, non-parametric, and every variable contributes. That something like that happens. In this case, what you best hope is you do some kind of approximation of F into a low dimensional, but not arbitrary approximation, but not arbitrary approximation, but a sensible approximation. You have some kind of error bound, either deterministic or statistic, right? But there exists a large class of systems in reality. Systems are sparse. Sparse in the sense that not every variable contributes. You do have a very large number of variables, but not everyone contributes. And even some contribute. They contribute marginally. So these are the problems I'm interested in. Some variables do not contribute. Some variables contribute very marginally. So in other words, depends on applications, right? I may be able to find these variables. Some are not contribute, some contribute very marginally, and by eliminating these variables first, before identification, the system becomes low dimensional. Makes things much, much easier. That is what this one is about. So model selection before identification, or before anything, right? Pattern recognition, machine learning, whatever you call. So I have a large number of variables. Some are not, some do not contribute. Some contribute, but only marginally. How to identify this one? Okay. Turns out it's very important. What do you mean, contribute marginally? It all depends on your definitions. Different definition lead to different scheme, different conclusion. I'll give you an example. Okay. And if we can identify for your purpose, then first thing is, of course, identify the variable which do not contribute. That is a kind of relatively easy. And the contribute marginally is not that easy. The reason is, for example, very extreme case, two variables correlate. What do you mean one is better or one is contribute more than other? You have to look together, right? If 4, 5, 6, 10, hundreds variables, they correlate. They become, the issue become very tricky. Okay. Now, if we can do that, then we can rank the importance of each variable, right? That helps, but does not solve the problem. Because again, if they're correlated, maybe let's say two variables identical or more or less same, so you can pick one and you can pick other one, right? In terms of importance, if you consider individually, both are important, but you can consider they're together. Only one is important. So it's a very tricky. And so best way is here. This is a kind of like hard problem. Given a performance requirement, let's say in my case, I'm interested in most cases is the goodness of fit, which is suppose the purpose of model is for prediction. Okay, so goodness of fit is very popular. Suppose let's say given, I have a minimum requirement. Given a nonlinear, non-parametric system, high dimension, can you give me a number of variables, minimum number of variables, which is required to satisfy this goodness of fit, let's say, or other performance? And then, what are they? Right? Eventually, what is the function estimated based on these n variables? So the difficulty level gets harder and harder and harder. So let's look at the first question. And I just give you an example. Let's say in system sensitivity literature, the derivative is important, definitely, right? Derivative give us idea of sensitivity. If derivative is larger, it's more sensitive to this variable. But we are looking at the global one. So E stands for the average. So average of the square term of the derivative, this is very often used in sensitivity literature, which makes perfect sense. And in system allocation and others, if a prediction is a concern, then this is so-called goodness of fit. So this original signal output, this estimated signal, the difference, right? This is a square term, and divided by, so it's a kind of relative scheme. 1 minus this term. So the best one, of course, y equals y hat. Then it's 100%, right? So we want this to be higher. And in like learning or pattern recognition, mutual information is often used, or some variations. There are many variations. Okay, so I just listed one discrete time version. You can use a continuous way. It doesn't matter. Okay, so let's look at the three different performance requirements. So is to see, are they consistent? If they're consistent, then I don't have to worry about any other, just pick one, right? If mutual information, good, then I use mutual information. If they are not consistent, then you be careful. You have to design your scheme, depends on your application. Right? Okay, so let's look at a very simple example here. This is a very simple nonlinear system, only one square term with two different coefficients, alpha 1, alpha 2. So I have two sets of different alpha. And the exact numerical value is not important. What is important is inequality. They're not consistent. So this tells us when you design a variable selection algorithm, keep in mind what is your goal. You want to do prediction, fine, use one. You want to do global sensitivity, use different one. So there's no one algorithm which applies to everything. Even though the concepts, ideas, some techniques are similar, but the conclusion is different, right? Okay, so that is the first lesson I learned. It's kind of like natural. I mean, once you carefully think about that, yes, application is different. Of course, they're different. Okay, all right. So now let's see what we do. So we presented some result schemes. One is based on very kind of intuition. Okay, so suppose let's say everything is fine. The system is very smooth, so we don't have to worry about the regulation or anything. Derivative exists, right? In some cases, derivative does not exist. So if the variable y output does not depend on particular xi input, you can say derivative of y respect to this particular variable will be 0. Because they are independent, right? Does not depend on. So naturally, the first one is, can I take some average of the derivative square? The p is the density function. If that's 0, average is 0, definitely it's 0, right? This actually if and only if condition. Now this turns out this is not very easy to calculate. The reason is we don't know f, we don't know square, or we don't know derivative. So is there any easy way to find out whether this variable contributes or not? So we look at this one instead of this one, average of derivative instead of average derivative. Now this comes to something very interesting. We started with, in this paper, I think not this paper, actually before, not the previous paper, look at the derivative at each point. The reason we were thinking is for nonlinear system in general, even dimension of system is not fixed. Some variable may contribute at some points, but does not contribute at other point, right? You always can construct a nonlinear system. So we thought, hey, let's start with locally. But it turns out if you have a high dimensional system, identification locally means only the local neighborhood data can be used. This again, you have a cost of dimensionality problem. It's unavoidable, right? So we're looking here is assume the dimension is fixed for the nonlinear system, then we can use average of derivative here. Average of derivative. Of course, you can see if the y does not depend on xi, this guy is identical to 0. So of course, average is 0. But this is not sufficient condition, right? It's an only necessary condition. So after that, we will have to discuss how good this necessary condition is. If this necessary condition is very loose, it doesn't mean anything. Right? Okay, so but let's look at this, how to do that. This one turns out very easy by integral, by parts. You can find the analytical one. Only the unknown is the derivative of, the unknown is the density function. Of course, we don't know density function either. And the derivative of density function. And there are many ways to estimate that. So we design another one. So we design, by the way, we only have a sample data, right? So we designed the estimate in this way. The density function, the derivative of the density function, and we can prove that converges with probably 1, as n gets larger. Then we define the derivative. This is the estimate of the average derivative. So this is computable. If you have data, it's computable. And the next step is to see how good this estimate is, right? And it is convergent. And we have these expressions. So this is what we want. And this is what we calculate. We have everything here. And then we can say, hey, the difference goes to 0 asymptotically. This is P simply means improbability. So we have analytical result, okay? So we can estimate the average of the derivative, okay? So average of the derivative tells us something about whether this variable y depends on xi. But still, it's not a sufficient condition. It's a necessary condition. Then the next question is how tight this condition is. So we look at the scalar case, and it's true for vector case. We look at the class of nonlinear systems. It's let's say polynomial. Can be any order, doesn't matter, any order. So if you fix order, then the polynomial can be written in terms of coefficients, right? So there are some conditions, basically the well behaved with bounded movement, etc., etc. Then it turns out if the derivative, average of derivative equals 0, for most of the polynomial functions except a major 0, this becomes also necessary, a sufficient condition. So in this sense, it's not only necessary, but it's very tight. It's not true only in a major 0 set. And of course, you can improve that by not the average of df dx, but you can add x here, average of x times df dx, and x squared times df dx, etc., etc. So make that tighter. But theoretically, you're just trying to make this major 0 set smaller and smaller, right? It's already a major 0. So you can make the 0 set 0 small. Okay. So that's the first approach we took. Then second approach, we took is based on very, very simple idea. It's a conditional probability, basically, or conditional covariance. Idea is follows. Suppose, let's say, y does not depend on x. I have output that does not depend on this variable, x. Then y and the y conditioned on x are the same, right? Because y has nothing to do with x. So that gives a way to check whether y depends on x. But we don't want to do that in this way. The reason is, so this is a given x, right? This is a function of x. If let's say average or variance, doesn't matter. It's a function of x. Now x is a high dimension. We assume high is x dimension. Otherwise, we don't have to do everything here. So we do this called inverse. Inverse means we don't study y given x. We study other way. We study x given y. Same thing. But the dimension is much lower because y here we assume is one dimension. So even though both way, I mean, ideally, in terms of the thinking, they're exactly the same. But numerically, this one is much easier to deal with because it's one dimensional. Even though x is high dimensional. So this is the whole idea behind the scheme. Then we look at the conditional variance. And the variance of x and the variance of x given y. If y depends on x, the two variants are different. If y does not depend on x, then their variance is exact same. So what we have to calculate is a conditional variance and a variance. Okay. We have algorithm. I don't think I have to go through. And only the result is some condition. Then if we have some indicator, then in probability we can say if y does not depend on x, then this lambda will be 0. And then if y depends on x, then lambda is not larger than 0, average. So we have a way to check. Okay, but the idea is a conditional probability based on. Okay, and by the way, this algorithm itself, the inverse contour is numerically expensive. The complexity is n squared. And there are other ways, we have other ways to reduce the complexity with exactly the same idea, but a slightly different approach. So you can reduce the complexity, but that's minor at this point, right? Okay. Now, the third problem is tough, very tough problem. Given a performance measure, here performance measure, I use the goodness of fit. Can you give me the minimum number of variables which achieve the performance? The second question, of course, what are these variables? This is a nonlinear, non-parametric setting. We don't know f. Right? We do assume some smooth conditions. So what we do is to recast this problem in the space of the producing kernel of Hilbert space. Okay, so that's why I guess it's very hard to see here. So let me just go to the other slides. It might be easy to see. Okay, because we don't have knowledge about f. F can be anything. So we use this producing kernel Hilbert space. And because we use this kernel space, we don't have much actually condition on the stability, on the probability. Only the well-defined this kind of things. Okay. And then we are able to develop a numerical algorithm to calculate that. Okay. So let me give you. I have a few minutes. Describe our idea. So again, I don't want to give you any proof, only ideas. If you're interested in proof, you can look at the paper, or I can send you email your paper. So let's see, S is a set of everything. And the T is a subset of S. So the number of T is less than Q. Q is the number of S, okay? Then we indicate X subscript T as a variable in the subset of T, okay? Then Ft is a restricted function, restricted into the space of Ft. And the space generated by the kernels, okay? So the notation is if I have a T, I substitute this guy by here. So if I allow use the M variable, okay? So that is a setup. Now, this is the goodness of fit, right? I want to find the given number of M. I want to find the maximum M, not M is the fixed, the optimal, this variables, number of variables, right? I think it's not number of, number is given. I find the best combination of variables so that the estimate belongs to the space as a maximum goodness of fit. That is my goal. Of course, this is a trivial, you can see that this is what we have. Now, it turns out this solution is not unique, which is intuitively clear. You may have two different sets that achieve the same performance. So I define the set of solution set. This is a solution set. It's anybody which can achieve the maximum goodness of fit is a one solution. Okay. Now, what we want, of course, we want to solve the problem based on available data, sample data, right? We only have sample data. We don't have anything else. Okay. So eventually, you have to algorithm which is implementable based on the sample data. Okay. And with a little bit of mathematics, and we construct some matrix, etc., etc. Then we try to solve this one, this minimization problem. So everything here is based on available data. The data is given, so we can construct. Then our result is if you can solve this problem with the proper choice of epsilon is here. Epsilon has to go to 0, but the square root of n times epsilon n goes to infinity. Then if you can solve this problem, the solution with the probability 1, eventually not in probability, this is a member of the solution set. So if we solve this problem, if n is large enough, we have a solution. So this solution means it gives you not only the minimum number, but it tells you what are these n variables which achieves the requirement. Okay, now you can see obviously here, this problem is not easy to solve. This numerical problem is not easy to solve. It's an integer problem. This is a numerical way, right, to describe this one. And it's an integer problem. That's hard to solve. So what we tried this one. Of course, if a number is not too large, we can use exhaustive method. And but if a number is large, we use this relaxed one. Basically, it's no longer 0 and 1, but between 0 and 1, the summation equals to n, or less or equals n. But we pick the largest as n, as a 1, and then rest as a 0. And there's some simulation, actually. I did a simulation with 800 points with 6 variables, but only 3 variables that contribute. Other 3 do not. Okay. And simulation seems to work very fine, I guess. We carry out 100 Monte Carlo simulations, and you can see if you pick one, this is the integer program, and which picks every the right program, right variables every time. But for the relaxed one, it's not so. For example, it will be confused if you have more than 3, not even 3. That's right, 3 is okay. Everything is perfect. If more than 3, you can see the difference, right? Okay. Anyway, so that is so this is kind of interesting. I think everybody in the education knows, I mean, even engineering knows. You want to find the simplest model to describe the system, right? As long as that's good enough. We don't want to use a more complicated one. So in this picture tells us we have 3 variables, contributes. Other 3 do not. Now you pick one variable, of course, the goodness of fit, which is performed really bad. Now if you go to the 2 variables, it's much improved. Because 3 variables, it improves a little bit. It means the 3rd variable actually picked contribute only marginally. You can, if you like, you can neglect this one. Now, if you go beyond the actual numbers, the performance does not get better. It actually gets worse and worse. The reason is it becomes noise. Now, what you are doing is trying to model noise, not the system. Right? That happens all the time. People realize. So don't use a complicated model if you can use a simplified model. Okay, so my time is up. Thank you very much.